Good morning. Thank you for joining us. My name is Sandy Breimer, and I'm one of the librarians here at the Mission Viejo Library. And I'm excited to present this program. I should say, I'm not presenting. I'm not smart enough to present what's about to be presented. Or I should say, I'm not the expert to present on our topic. That's Richard Stember of Science Heads. Just a couple things to point out. This is part of a grant project. And actually another part of the grant project is we've got some STEM activity kits that are available for patrons to check out. The one that ties in with today's presentation is called the Sun and Moon Activity Kit. It's got some sinoculars, some binoculars, it's got some craft activities, building a sundial, some different UV things. It's a fun way to get your hands on some equipment that you don't necessarily want to purchase. You can now check it out from the library. They'll be available to check out or place on hold starting this afternoon. So if you have any questions about that, feel free to email libraryprograms@cityofmissionviejo.org, and I can get you set up on how to check out one of those activity kits. And then I just wanted to tout summer reading is going to be back and starting June 15th through the end of July. So keep an eye on our webpage for that. And then I'm going to turn this over to Richard. We are going to ask if you have any questions during Richard's presentation, please put them in the Q&A and he'll address those at the end of his presentation. So Richard, it's all you.
Thank you very much, Sandy, and thank you for having Science Heads participate in today's presentation. My name is Richard Stember, and I'm the Executive Director of Science Heads. We're a local 501c3 nonprofit, and we make STEM fun. We bring STEM activities to schools and libraries and museums and the public through events like we're holding today. And today we're going to be talking about the life of stars, a subject which is near and dear to my heart because besides being a chemist, a scientist, I'm also an amateur astronomer. And I love looking at stars and other astronomical objects through the telescope at night, and also through our special solar telescope that we'll be using a little bit later today to view the sun in real time. So with that, let's talk about stars. First off, let me define what is a star. Actually, a lot of what we're going to be talking about today may come as a surprise to you. You may think you know what a star is, or think you know how long a star lives, but I may have some surprises to share with you in today's presentation. So first off, what is a star? So a star is a ball of hot gas. You probably have heard that before. And it's held together by gravity. And we all know what gravity is. It keeps us from floating away into space, doesn't it? And a star is powered by nuclear fusion. Our sun, of course, is a star, the nearest star to us. But near is that term is pretty relative. Our sun, on average, is about 93 million, that's million with an M, miles away from us. So it is pretty far away, and it's the closest star. This graphic that I'm sharing with you shows shows a cutout of the major components of a star. It has a core where the nuclear fusion occurs. It has a radiative zone and a convective zone, and we'll talk about these a little bit later. But the gravity that I referred to compresses the gas in the center of the star. It makes it so dense and hot that the nuclei of atomic molecules combine, and that's mostly hydrogen that's combining into the compound helium. or the element helium. And that's what we refer to as nuclear fusion. That process creates a lot of energy. In fact, many scientists around the world are trying to harness that energy so we can generate electricity from it instead of, for example, fossil fuels that we use at our power plants currently. It's this nuclear fusion that makes stars hot and bright. And that energy travels out from the core to what we call the star's surface. Now, a star doesn't actually have a surface. There's nothing that you can put your feet on and walk around if you could survive the high temperatures of a star. What we call the surface is really what we call the photosphere. That's where the light emanates from the star. And when we look at a star through a telescope, for example, it looks like it has a surface. It's really just where the light is coming from, where it's radiating out into space. There's in fact many different types of stars. And when we talk about the life of stars, well, each of these different types of stars have different life cycles. So let's first talk about the different types of stars and what makes them different. So you may have many times looked up at the night sky, and here in Orange County, where we've got a lot of light pollution from local cities and street lamps, we see a few hundred to a few thousand stars in the night sky, depending on how dark it is. If you get up into the mountains or out to the desert, you'll see many more stars because there's a lot less light pollution, and your eyes, once they've adapted to the darkness, are great sensors for looking at stars, for seeing those stars. Well, the stars that you've looked at night pretty much all kind of look the same, but you may have noticed a few of them have different colors. So as we look at pictures today, most of these images have been captured with space-based telescopes like the Hubble telescope. You'll notice a lot more color, and that's because the cameras or imagers on those telescopes are collecting light over a long period of time, and the colors really jump out in the images that way. Our eyes, even when they're night adapted, aren't able to see a lot of color at night. But you can see some color in stars. One of my favorite constellations to look at, and it's setting kind of early right now, so it may be hard to see this time of year, is the constellation Orion. You may recognize Orion. There it is in the middle with its 3 stars that make up its belt. It's a hunter, according to ancient Greek lore. The star Betelgeuse, up in the upper left corner there, you can see some reddish color, orange color, when you look at it with your eyes at night. So there's an example of a star that you see at night, and you can detect with your own eyes some color. But in fact, when we look at stars through telescopes, we see a lot of different colors. And we're going to talk about what scientists call mass, and how a star's mass determines its color, its temperature, and its lifespan, and ultimately what's going to happen to that star. Now, what do we mean by mass? Well, that's a term that scientists use to describe the amount of stuff in an object. For example, if I've got a rock in my hands here, it has a certain mass. Now, here on Earth, I can take a scale like this postal scale and weigh this rock, and that tells me how much mass that rock has here. And the scale is telling me it weighs about 13 ounces. But let's say I was somehow magically transported to the moon. The moon has a lot less gravity. It has about only 17% of the Earth's gravity. So that scale would no longer read 13 grams. It would read something much less than 13 grams. The rock didn't change. What changed was where I'm weighing it. So it's that characteristic of the rock that's not changing that we refer to as mass. If I was to take a rocket ship to Mars, Mars has less than 1/2 the gravity of Earth. So again, it would weigh a lot less on Mars, but the rock hasn't changed. It still has the same amount of mass. So we work here on Earth, so we refer to the mass of that rock, for example, being the same as its weight. But out in space, we can't use that same scale, but we refer to the mass in the same way. So it has 13 ounces of mass, for example. Stars, of course, are much more massive. They have a lot more stuff. They weigh a lot more if we were to move them here to Earth. And it's that mass that determines its ultimate fate. So, but that's not the only thing that determines the fate of a star. We're going to take a look at a couple of stars that maybe you've never seen with your own eyes, but we can see through a telescope here. This is a star called Alberio, or Alberio is the proper way to pronounce it. Now, you may be saying, well, Richard, wait a minute, there's 2 stars there. In fact, there's a lot more. Alberio, when we look through a telescope, when we look at it with our eyes, if we know where to find it, it looks like 1 star. When we look at it through a telescope here on Earth, it resolves to 2 stars. So it's actually 2 stars that are very close together. We call the one on the right Alberio A, and the one on the left Alberio B. These 2 stars are about 430 light years away. That's another amazing thing about astronomy. When you're looking up at the night sky, you're actually looking back in time. So that light left the star 430 years ago, and it's just now reaching our eyes. For all we know, that star could have long ago exploded. We wouldn't have known about it for another 430 years because of the distances involved. Now, these 2 stars, Alberio A and Alberio B, are very, very close together in the sky. But they are actually pretty far apart physically. We don't know quite how far apart they are physically. But when we look at it in the sky, they take up a very, very small a very small slice of the night sky. We can measure that slice. It's 34.5 arc seconds. What's an arc second? Well, think of this. If you hold up your pinky at your arm's length and hold it up to the sky, that's about 1 degree of the sky. The sky, we split up the sky like a compass into 360 degrees in all directions. Well, your pinky is about 1 degree, and you can block out the moon with your pinky because it takes up about 1/2 degree typically in the night sky. Furthermore, we break up that degree into segments called arc minutes. There's 60 arc minutes in a degree, so it's kind of like a clock. A degree would be 1 hour, and there's 60 minutes in an hour. And then we go further, we break up an arc minute into what we call arc seconds, and there's 60 arc seconds in a minute. Well, Alberio and Alberio A and Alberio B, from our perspective here on Earth, is about 34 arc seconds in separation. In other words, they're very, very close together from our perspective. We think that one orbits the other and takes about 75,000 years to complete that orbit. But we're not quite sure. We don't know exactly how far apart they are. And we don't even know if they're gravitationally bound in that way. But from our perspective here on Earth, they certainly look very close together. Looking at this picture, this image from a telescope, we can see that Alberio B is bluish. It's got a blue color. It's what we call a hot blue white main sequence star. Scientists get very, very specific with their classifications. A lot of science is all about classifying things, of course. So it has what they refer to as a spectral type, B8VE. It is about 3.8 3.8 times the mass of our sun, almost 4 times more massive than our sun. And it's about 2.5 times larger than our sun. That blue star, Alberio B, has an average surface temperature about 13,200 Kelvin. Now, Kelvin is related to the Celsius scale. You may have heard of Celsius. That's what they use in Europe, for example, to report temperatures. Kelvin is equivalent to Celsius with a slight adjustment. 13,200 degrees Kelvin is the temperature, the surface temperature of Alberio B. Compare that to our sun. Our sun is only about 5,500 Kelvin. So it's a much cooler star, our sun is, than Alberio B. And in fact, bluish stars tend to be hotter. Alberio B is also 230 times brighter than our sun. And it's much younger. It's only about 100 million years old. Now, wait a minute. You're thinking 100 million years old. That sounds pretty old to me. Our sun is expected to live, quote unquote, for about 10 billion years. And we'll talk about the lifespans of stars in a little bit. Our sun is about 4.6 billion years old. Billion with a B. That sounds pretty old, but it's actually not so old when you compare it to some other stars out there. The other star that we see in this image, Alberio A, is what we call a reddish yellow giant, spectral type K22. It's got about 14.5 times the mass of our sun, 14.5 times more mass. And it's about 69 times larger than our sun. But it's a lot cooler than our sun. Alberio A average temperature is about 4,270 degrees Kelvin. Again, our sun is about 5,500 Kelvin. But Alberio A is brighter, about 1,200 times brighter than our sun. So you can't always tell about a star by just looking at it. And I'll explain why in a little bit. So why do these stars look very different? What's different about them to cause the changes in color and brightness and temperature? Well, this is where astronomers struggled for many, many years. And like all sciences, they started by classifying the subject that they're studying. You know, biologists classify species and genus and animals and plants and bacteria and such. Astronomers classify stars and other types of objects. And they came up with this classification that you see shared here based upon roughly the color of the star. OBAFGKM. Now, when I was in school, we would remember this series of letters using a mnemonic. OB, a fine girl, kiss me. Now, that's probably been modernized since, based upon your preferences, and there may be other mnemonics that are used, but that's how I remember it. Oh, be a fine girl, kiss me. It never worked though. I never got a lot of kisses from girls in college, so they thought I was too much of a nerd. So we classify stars based upon their color, and their color is key to the temperature, the surface temperature of the star. Notice the O type of stars are much hotter, about 25,000 degrees Kelvin, than the redder stars, which are only about 3,500 degrees Kelvin. Another way they classified or studied stars is by putting them on a scatter plot diagram that we see here. Along the bottom there is temperature, the average surface temperature of the star, from hotter on the left to cooler on the right. Hotter is bluer, cooler is redder. And we also plotted on the left there luminosity. Now, luminosity is how much light the star puts out. Think of a flashlight, for example. You put new batteries in a flashlight, it's going to shine very brightly. As those batteries age, though, get older, the flashlight is going to get dimmer and dimmer. That would be a measurement of luminosity, how much light the flashlight is giving off. And not all stars give off the same amount of light. So if we compare luminosity to temperature, we get a diagram like this. It's called the HR diagram. And we see that luminosity depends not only on the star's color, but also on the size of the star. We can see relative sizes of stars here. We look at the top there, what we call supergiants. They're much larger than our sun, which is labeled there in what we refer to as the main sequence. And our sun is much larger than, in the lower left portion of this HR diagram, what we call white dwarfs. And there's giants and other types of stars as well. Luminosity is relative not just to the temperature, but also to the size of the sun. Bigger stars, giants and supergiants, have larger surface areas. They're physically bigger, so they can put out more light. Think of a spotlight that would be used, for example, at a movie premiere. It's huge. You couldn't put your arms around it. It puts out a lot more light than your handheld flashlight, doesn't it? Stars like our own sun fall on what we call the main sequence. These are regular sized stars, average type of stars. They're in their stable stage of their lifespan. So our sun is relatively stable. Not all stars are, by the way. And we'll see what happens to an unstable star in a little bit. Now, I've labeled some stars on this HR diagram that maybe you've seen with your own eyes or are familiar with. Betelgeuse. You remember the constellation Orion that I shared with you a moment ago? Betelgeuse, in the upper left shoulder of this hunter, is a supergiant, a red supergiant. And we see the red color very faintly when we look at Betelgeuse. Rigel, in the opposite corner of the constellation Orion, and it's on his left foot, is a bluish star. And we can see that in the HR diagram to the left of Betelgeuse. It gives out a lot of luminosity. Both of those give out about the same amount of light. They're much more luminous than our sun is. But remember, distance plays a role here as well. I mentioned at the beginning, our sun is about 93 million miles away on average. It's obviously a lot closer to us than either of these stars, and therefore our sun appears much brighter to us. But that's a trick. So the closer you get to your flashlight, the brighter it's going to look. If you put your flashlight a mile away, its luminosity hasn't changed, but it's farther away, so it's going to look less bright, isn't it? It's going to look a lot dimmer. So these stars are at much different distances, our sun being the closest of these three that I'm talking about. Betelgeuse and Rigel are both pretty far away. Another star that maybe you've seen in the sky is Sirius. And we see that in the middle of this diagram. Sirius, like Alberio, is actually multiple stars that are very close together. We see it as one star, though, because they're very close together from our perspective here on Earth. We say that Sirius is the brightest star in the sky. Well, wait a minute. It's much less luminous, according to this diagram, than Betelgeuse and Rigel. And again, that's because Sirius is much closer to us than either of those stars. Sirius is about 8 light years away, which means the light that we see tonight left Sirius 8 years ago. By comparison, Betelgeuse is 860 light years from us. So its light left that star 860 years ago. And that's why Betelgeuse looks much dimmer, even though it's much more luminous. It gives off much more light than Sirius does. So you may be wondering, how much bigger do stars get than our sun? Both Betelgeuse and Rigel are supergiants. Let's see if we can do a size comparison here, just for fun. So here's some stars that maybe you've seen with your own eyes. Antares is a star that's easy to see at night. Betelgeuse, I mentioned, in the constellation Orion. Aldebaran, Rigel, Arcturus. They're progressively smaller in size. How do they compare to the sun? Well, I'm going to see if I can draw the sun here. It's right here in this slide. It's about 1 pixel size on this slide, one small little dot. That is the comparison of our sun right here to the star Antares and Betelgeuse, which are huge by comparison, physically much larger than our sun. And Antares is not the largest star that we've discovered. There's even bigger stars than that. So these sizes are quite dramatically different, aren't they? And remember, size plays a role in luminosity, as well. So let's go to another star, or another question. How come some of these stars are so much bigger than others? Well, that gets us to life cycle. And this is what today's topic is all about, the life of stars. So to simplify it, I'm sharing this graphic here, which shows basically 2 life cycles of a star. And our sun, being an average star, follows the life cycle that you see at the top row here. They all start with a stellar nursery, a nebula, a cloud of matter in space that coalesces and forms into a star. And from there, depending on how much mass the star has, they follow different paths. Let's talk about stellar nurseries first. Here's a very famous image that the Hubble telescope took a number of years ago. It's actually several hours or days worth of images combined together. It's referred to as the pillars of creation. Amateur astronomers call it the Eagle Nebula. And to me, it looks like an eagle flying straight up. We can see its claws here, and we can see its wing, one of its wings here, and we can see its beak and its head here. So kind of looks like an eagle. Well, the Eagle Nebula is about 55 million years old. It's a cloud of gas and dust in space, stretching about 70 light years by 55 light years. And it's actively forming new stars. It's a stellar nursery. Stars are forming mostly around the edges of the pillars that you see here, where it's really bright. These are the star forming regions of this stellar nursery. It's about 7,000 light years away. It's in our Milky Way galaxy, and that's why we can see it, even with Earth-based telescopes that are large enough. It's in the constellation Serpent. And there's thick regions of gas and dust. So much of it is blocking light from the stars that are embedded in this nebula. So those dark areas are actually very thick regions of gas and dust that the light cannot shine through. Particularly in the claw area, you see a lot of dark gas there. Eventually, that dark matter, I shouldn't say dark matter, that matter that's blocking the light will coalesce and form what we call protostars, and they'll continue to compress and eventually form into what we refer to as a star. Nuclear fusion will start in the center, and it starts giving off light, shining like a star does. And that light actually will push away the surrounding gas, and the star emerges, if you would, from its nursery. That can take millions and billions of years to occur. That light, by the way, shines on the gas and dust in the nebula, and we can see many different colors in there. And those colors are key, or a key to the type of elements found in the nebula. Astronomers will use a technique called spectroscopy, and that is breaking down that light so we can determine what elements are in the clouds. So getting back to our own star, our sun, it formed in a cloud similar to this one. But what happened after it was born? So we can try to compare the life of a star to a human itself and its life expectancy. You know, kind of like what we do with dogs. We say, we ask, how many dog years is that? Well, I've heard it said that, 1 year is like 7 dog years. I don't know if that's accurate or not. I'm not a veterinarian. Obviously, with stars, we talk about millions and billions of years. A human typically lives 80 to 100 years of age. But this graphic here makes that relationship. So a protostar, the early stage of a star forming, you can think of as a fetus in a woman's womb before the baby is born. When fusion starts, the star progresses from a toddler to a young child up to a young adult. And then that's basically where our sun is right now, being an adult. It eventually will get old enough, like all of us, and will will become middle-aged. And for our sun, it will turn into what we refer to as a red giant, like Betelgeuse in the constellation Orion. And then at some point in time, that star will die. It'll pass away. It'll turn into what we refer to as a white dwarf. So this is the life expectancy of our sun. Right now, our sun is about 10.6 billion. I'm sorry, 4.6 billion years old. It's about halfway through its life cycle. It'll live a total of 10 billion years, we believe. And that's a pretty average life expectancy of a star. Well, what happens at the end? What will happen to our sun? This image here is a great example of what the fate of our sun about 6 billion years from now is. This is an image of a planetary nebula called the Ring Nebula. And using our telescopes, Science Head's telescopes, we look at the Ring Nebula all the time. It's near the star Vega in the constellation Lyra. It's an example of the fate of our own sun. I mentioned our sun will eventually turn into a white dwarf. And in this image, we can see a white dwarf in the center here, a very dim star. And on the outer, outside of that, we see a cloud of gas. Now it looks like a ring. The cloud is actually a sphere all around that white dwarf, but it's a very thin cloud. In fact, it does not block any light, so we can see through it. And so we don't see the cloud that's the part of the cloud that's facing us. We're literally looking through it, but we do see the edges of the cloud, and it looks like a ring. This Ring Nebula is about 2,000 light years away. And it is the remnants of a star, much like our own sun, that was at the end of its life cycle. Eventually, the white dwarf at the center will radiate away all of its heat, what's left there. Until it does so, this Ring Nebula is a beautiful object to look at, because the light that comes off of that white star creates all these colors in the gas. Now, in fact, this has been enhanced. The colors have been enhanced to illustrate the nebula's composition. The deep blue color in the center is helium. Remember, that's what a star fuses. It fuses hydrogen together into helium. So that's where a lot of the helium went to. The lighter color is hydrogen and oxygen. The reddish color is from nitrogen and sulfur. The star produced all of those different elements. And again, that white dwarf in the center, over billions of years, will get cooler and redder until it's not shining anymore. And the ring will stop glowing in these colors because there's no energy there to excite the atoms there to produce the colors itself. So that's the fate of our sun. Somebody far in the future may be looking at a telescope one day and discover a nebula, much like the Ring Nebula, and that will, billions of years from now, they will have discovered that, and it'll be the remnants of our own sun. But no need to worry. I'm sure by then we'll find another star to live around, so we don't have to worry about our sun conking out anytime soon. So that's an example of an average star, where it ends up. What about those supergiants, those more massive stars? What happens to them? Well, this is where it gets really exciting. So if we consider the bottom path of this life cycle that I'm sharing with you. That blue massive star, which also formed at a stellar nursery, will eventually turn into a red supergiant. And that supergiant can explode into what we call a supernova. And that supernova, depending on the mass of the star, can produce either a neutron star or a black hole. So let's back up for a second and talk about the mechanism of all of that. So a star like Rigel, a blue giant star, formed in the same way as our sun did. And it's burning hydrogen, it's fusing hydrogen into helium, but it's more massive, and it's doing so much, much quicker than our own sun is. And then that much faster than other main sequence stars. It's going through that fuel only hundreds of millions of years, not billions of years. And eventually it's going to run out of hydrogen fuel. It's kind of like the difference between a sports car and a Volkswagen Beetle. They may still hold the same amount. Their gas tanks may hold the same amount of gasoline, but that supercharged engine in that supercar, that sports car, is going to burn through that gasoline much quicker. Well, that's what Rigel is doing. It's burning through its hydrogen fuel much, much quicker. And eventually it'll run out. And when it does so, it'll start collapsing. And that collapsing center gets then hot enough to fuse the helium that it was producing with the hydrogen fusion into heavier elements, into carbon, oxygen, silicon, sulfur, calcium, all the way up to iron. Amazing thing to think about. This is where iron comes from stars. And you may know that your blood consists of what we call hemoglobin. And in the center of those cells or globs of hemoglobin is the element iron. Your blood contains iron that came from a star, most likely a star that went supernova. We're made out of star stuff, in other words, as Carl Sagan used to say. Keep that in mind. So this Rigel will eventually start producing these heavier elements, right up to iron. And the outer layers start expanding as it does this and cooling down. And Rigel, like all these supermassive stars, will turn into a red supergiant. But this fusion into these heavier elements cannot continue forever. They're no longer stable. The more heavier elements at the core of the star is producing, the core becomes unstable, and it cannot produce enough energy to counteract the gravity that's pulling the star closer and closer together. And the core begins to implode. That's the opposite of explode. Implode is crushing down. But unlike the smaller stars, when a really massive star collapses, the iron in its core absorbs energy, causing the core to collapse even faster and faster. And the atomic nuclei in the core can no longer resist the force of this collapse. In less than a second, less than 1 second, the density of the atomic nucleus collapses, and we call this ultra dense collapsed core a neutron star. These are no longer elements as we know them. These are now the particles that make up elements, neutrons. And when the core reaches this ultimate density, it resists any further compression and bounces back. And this rebounding core creates a shock wave that tears through the star's outer layers. And the heated gas starts expanding outward at extremely high speeds, about 5% the speed of light. This rapid implosion of the core ultimately triggers a huge explosion of the star's outer layers, and this is what we call a supernova. But there are certain stars that are so massive that something else happens. I'll tell you that in just a moment. But let's think about neutron stars for a second. How do we know they exist? How do we know that they're really out there? Well, we detected them a long time ago. Some of them are shining a light in specific directions along the poles of their rotation, and some of them are rotating very, very, very quickly. If we happen to be just in the right position in the sky, by that I mean the Earth, we can detect flashes of light as they rotate, and that light pulses. Some of them also generate radio waves and other radiation that again pulses because the neutron star is rotating so fast. So it's not like a regular star where the light is emulating in all directions. The neutron star, the light and the radiation coming from it are going out along the poles of the star. Pretty interesting stuff. Well, I mentioned if a star is massive enough that its supernova can produce something else. And you've all probably heard of this. We call it a black hole. It's called a black hole because its gravity is so massive that light, even light, cannot escape it. So when we look at it, we don't see anything. But we can now start seeing something with our new telescopes, our powerful telescopes. And I'll show you an image, an actual image of a black hole in a little bit. But let's first take a look at the remnants of a supernova. This is a nebula that we can see even with ground-based telescopes called the Crab Nebula. And the Crab Nebula is near the constellation Cancer. Not quite sure why it's called the Crab Nebula. It doesn't look like a crab to me. But it does kind of have arms that are going all over the place. When this star went supernova, it produced this huge cloud in our galaxy, the Milky Way. And this was actually witnessed. People saw this happen. It's the results of a star that exploded on July 4th, 1054, over almost 1,000 years ago. And astronomers, ancient astronomers in China, witnessed this. All of a sudden, in the night sky, there was this huge star that appeared out of nowhere, and it was super bright. Some reports indicated that it lit up the sky, and you could read a book or a manuscript, just like it was the moon lighting up the night sky. This particular image, by the way, was taken by the Hubble telescope. 24 individual exposures taken over 3 months. So continuously, Hubble just pointed at this part of the sky, this very, very small slice of the sky. And for days and days, it collected all the light. 24 times over, and then the astronomers combined the images together. The orange filaments that you see there are remains of the star, mostly hydrogen, what little hydrogen was left before it went supernova. The blue or the outer parts, in the outer parts of the nebula is oxygen. You remember the heavier elements that helium gets fused into, oxygen is one of them. Green is ionized, singly ionized sulfur, and red is doubly ionized oxygen. And somewhere in the middle of this remnant, of this cloud, is a neutron star. Much more massive. That even that neutron star is much more massive than our sun. I'm sorry, it's about as massive as our sun, but it's much smaller than our sun. It's only about 20 miles in diameter. So imagine taking our sun and squishing it together and placing it right there in Mission Viejo. Our sun, to give you a reference point, if you were to add all the mass together of our planets, add to that all the mass of the moons that orbit around those planets, all the asteroids, all the comets, all the dust that's floating in our solar system, if you combine all of that together and compare that to our sun, what you would have would be just 2% of the mass of our sun. 98% of the mass of our solar system is in our sun. Jupiter can't compare to it. Saturn can't compare to it. Add that all together, only 2% of the mass of our solar system is in the planets and moons, etc. So imagine squeezing that 98% down to fit in the city of Mission Viejo. That's how dense a neutron star is. But even so, this pulsar, as we call it, this neutron star that's spinning rapidly, giving off radio waves and light, visible light, it's producing about 100,000 times more energy than our sun is. Huge amount of energy coming from it, but it's very far away. So I promised to show you a picture of a black hole. And there it is. This is a very recent image. First time, this is the first time that we've actually been able to take an image of a black hole. Now that light that you see there is not the black hole. The black hole exists in the center of that ring. It's actually a shadow of the black hole on the light that's coming from the area around the black hole. This is in the center of a galaxy we refer to as Messier 87. It's about 55 million light years from Earth, 55 million light years away. The black hole is 6.5 billion, with a B, times the mass of our sun. It's hugely massive. And to make this image, astronomers coordinated 8 ground-based radio telescopes around the world, combined their signals together through what's called interferometry to make it work like one big telescope the size of our entire planet. Now, you may think telescopes are just for light, but we have huge dishes that are used to take images using radio waves. And that's what these telescopes were doing, because the matter surrounding this black hole is producing a lot of radio waves. The black hole itself is an extremely dense object. And as I mentioned earlier, no light can escape it. The gravity is so great that light cannot shine from that black hole. Anything that gets too close to the black hole what we call the event horizon, will be sucked in by that gravity and consumed, never to reemerge, because of that huge amount of gravity. So by its very nature, a black hole itself cannot be seen, but we can see the material around it that's spiraling around the black hole in kind of a death spiral, eventually reaching that event horizon and gravity pulling in that material into the black hole. And that's the shadow that we see at the center of the black hole. Just recently, and I'm sorry that I didn't get a chance to add this to the slides, astronomers have taken a picture, literally in the last few days, of a star being sucked in and ripped apart into a black hole, spaghettified, as we call it, as its material is sucked away from the star itself and into that event horizon. So do a Google on a spaghettified star, and I think you'll find that image. It's amazing to see. If you want to learn more about stars and their life cycle, I invite you to go to our website. But here's also a couple of great links that from NASA. NASA Universe at science.nasa.gov. There's a whole section on how stars form and evolve. And there's some great videos of showing the life cycle of a star. So if you go to nasaclips.arc.nasa.gov, you can watch those videos as well. Now, as Sandy mentioned, this has been produced with a grant from the Institute, Museum, and Library Services. I want to thank them, and I want to thank the library at Mission Viejo for sponsoring us today. I hope that you found the topic interesting. I see we may have some questions there. And somebody's asked, do white dwarfs explode? And in fact, no, they don't. An explosion requires energy. And white dwarfs are rapidly running out of energy. So there's no energy left to cause an explosion. The white dwarf will eventually just cool off and stay in that kind of state until it completely runs out of energy. And all that'll be left is whatever heavy matter, iron, carbon, oxygen, etc., is left from the fusion that once was happening at the center of the star. So excellent question. Thank you very much. I look forward to additional questions. If you'd like, you're welcome to email us at info@scienceheads.org. We're happy to answer questions. Check out our links, check out our website. Hope you have a great weekend. Thank you. Sandy, I see we have another question here. Is Polaris actually two stars? Yes, Polaris is a binary system, and we see it as a single star because they're very close together, with our naked eye, but even an amateur-sized telescope can resolve them into the binary system. So there's a lot of examples of that, of multiple star systems that we see as a single star. So thank you for that question as well.
Okay, looks like I don't see any other questions coming up. Thank you everyone for joining us. It's very much appreciated. In just a few minutes over on Facebook, we're going to be doing a live STEM activity demonstration and something you'll be able to duplicate at home. It's really simple and just includes your own, probably stuff you already have in the kitchen. And so hop on over to Facebook at about 11:40 for that. You do not have to actually have a Facebook account. If you go to on your web browser, just www.facebook.com Mission Viejo Library. You'll be able to get in and see the live presentation. The activity is we will be showing you a very common grocery store item that can be used as a UV detector, and just how to kind of set up the little experiment. I don't want to give it away because I was surprised. I had no idea what it was. When it happened, I was like, wait, what? Anyway, so we'll be doing that. And then if you did see in the chat, we do have a survey because this was a grant project. We do have a participant survey we would like you to complete if you can. So that would be appreciated. And then after our STEM activity, join us back again on Zoom, 12:15. We'll be with Richard again doing the live solar viewing, which should be pretty fascinating, and hopefully it'll kind of bring together the lecture part you guys just kind of all learned about, and we'll be able to see some of that in action. So with that, I am going to sign off on this. We're going to hop on over to Facebook and then hope to see you again on Zoom at 12:15. If you need that link sent again, email libraryprograms@cityofmissionviejo.org real quick, and we will get that to you just before the 12:15 session starts. So thank you and see you soon.